In lesson 6.3, we're going to talk about complex rational expressions. The easiest way to define what this would look like would be when you have a fraction in the numerator and a fraction in the denominator. So kind of thinking about a fraction over another fraction. So we're going to talk about how to simplify these. And it's going to come down to finding the LCD, the least common denominator. So go to your denominators. We have a denominator of 2, a denominator of 4, a denominator of 6, and the denominator of 8. So we're going to break these down into prime factorization. So 2 is 2 times 1, 4 is 2 times 2, 6 is 3 times 2, and 8 is 2 times 4, and 4 is 2 times 2. So the greatest number of times that 1 occurs is once, the greatest number of times 2 occurs is 3 times, and the greatest number of times 3 occurs is once. So your LCD would equal 1 times 3 times 2 times 2 times 2, or 24. So what we're going to do now is we're going to multiply each numerator by 24. So we're going to have 1/2, and we're going to times it by 24, plus 3/4, and we're going to times it by 24, over 5/6, and we're going to times the numerator by 24, minus 3 times 24 over 8. Okay, so when we multiply, we can now have, we're going to put this in the numerator. So now we're going to simplify our parts. So I know that 24 goes into 2 12 times. I know 24 goes into 4 6 times. I know 24 goes into 6 4 times. And I know 24 goes into 8 3 times. So by multiplying by your LCD, you've now eliminated those extra denominators. So in the top, I'm left with 12 plus 3 times 6. Now I have just one fraction because this denominator is gone. And on the bottom, I'm left with 4 times 5 minus 3 times 3. So I'm going to have 12 plus 18 over 20 minus 9. So I'll be left with 30 over 11. Okay, so we can take a complex part and we can make it into one fraction. Okay, if we look at example number 2, find your LCD. So I have a cubed b, which is going to be 3 a's and 1 b. I have a single b. I have a squared b squared. So I would have 2 a's, 2 b's, and I have a b squared, which would be 2 b's. So the greatest number of times that a occurs is 3 times, and the greatest number of times that b occurs is twice. So my LCD would be a cubed b squared. So I'm going to multiply all my numerators by my LCD. So I'm going to have a cubed b squared times 1 over a cubed b plus 1 over b, and I'm going to times that by a cubed b squared over a cubed b squared times 1 over a squared b squared minus 1 over b squared times a cubed b squared. So when I multiply, I just have one numerator and one denominator. So a cubed and a cubed cancels out. 1b cancels out with one of these b's, so I have one remaining. 2 of those a's cancel out with 2 of these a's here, leaving me with one remaining. 2 of the b's cancel out with both of those b's. B squared cancels out with b squared. So I am left with, this b can cancel out with one of those b's. So I'm left with b plus a cubed times b over a minus a cubed. and just that we've learned, is that we're not finished until maybe you can't factor anything more else out. So I know in the numerator, I have a b in common. So I factor out the b, and I'm left with 1 plus a cubed. In the denominator, I have an a in common, so I factor out the a, and I'm left with 1 minus a squared. So I have a sums of cubes, and I have a difference of squares. Because 1 is a perfect cube, a cubed is perfect, 1 is a perfect squared, and a squared is a perfect square. So then I'm going to factor into my special cases. So a is 1, b is a, times a squared plus a times b plus b squared, which would be a squared, and since it's a positive sign, this should be a minus, over a times difference of squares, 1 minus a, 1 plus a, so our 1 plus a's cancel out, and I'd be left with b times 1 minus a plus a squared over a times 1 minus a. Okay, so again, you're not finished until you can factor out no more. So anything in common can only be 1 between your terms. Okay, so if we look at example 3. In example 3, again, we're taking that same principle, but now we're just stepping it up a little bit. So again, I would always factor first. Okay, so I have 3 over, my greatest common factor is a 2, so I'm left with an x minus 1, minus 1 over x plus 1, over 1 over x minus 1, plus x over x plus 1, x minus 1, difference of squares. So my LCD, the greatest number of times that a 2 occurs is once. The greatest number of times that x plus 1 occurs is once in my terms. The greatest number of terms that x minus 1 is 1. Okay, so there's my LCD. So now I'm going to multiply all my numerators by my LCD. So I'm going to have 2 times x plus 1 times x minus 1 times 3 over, and I'm going to leave it in factored form. And the reason why I factor is because it makes things so much easier to see when you're dealing with polynomials. So 2 times x plus 1, x minus 1, all over 2 times x plus 1, x minus 1, times 1 over x minus 1, plus x times 2 times x plus 1, x minus 1, all over x plus 1, x minus 1. Okay, so now comes the cancel out. So the 2's go away, the x minus 1's go away. The x plus 1's go away, the x minus 1's go away. The x plus 1's, the x minus 1's. So what am I left with? In my first term, I have 3 times x plus 1. Nothing is in my denominator. Minus 1 times 2 times x minus 1 over 2 times x plus 1 times 1 plus x times 2. Okay? So, let's distribute my terms over my binomials and then combine like terms. So I'm going to have 3x plus 3. Negative 1 times 2 would make negative 2. I would take your sign with you, so then you don't have to distribute twice, because if I'm subtracting more than one term, then that negative goes to everything. So I would distribute a negative